Hi everyone, so today we're going to be looking at calculating the concentration of not only the reactants but also the products when it is at equilibrium. So we're going to be looking through different cases that we could be using throughout questions like this. So for our first case here, we can be using the quadratic equation method. And so in this question here, it says, given this equation, calculate the three equilibrium concentrations when Kc is 0.0625 and the initial concentration of PCl, I don't know why that L is there, is 1 mole. So our first step always is to fill in the ice table. So given our information, we can fill this in. So we have 1 mole of PCl, which means we have 0 for our products. Our change in concentration, so our ratios is 1 to 1 to 1. We know our reactants is negative and our products is positive X, and therefore our equilibrium concentration is 1 minus our X, and then X and X. So given our table filled in, we can answer step 2. So using the Kc solve for X. So we know our Kc, we were told our Kc is 0.0625. So therefore, we have to write out our formula. So our Kc is going to be our products on top, PCl3, Cl2, divided by our PCl5. So from there, we can fill in our values, which was from our ice table, which was our change in concentration. We can fill in our X values. So we have X times X divided by 1.00 minus X. And then we can fill in our Kc value on the other side, so 0.0625. From there, if we were to expand this out, make sure we get everything organized, we have to multiply what is our denominator by everything on both sides. So we're going to multiply both sides by 1.00 minus X, which it's going to give us nothing on the right-hand side. It's just going to give us our numerator, which was X squared, because X times X is X squared. And then on the left side is 0.0625. And then in brackets, we get 1.00 minus X, and that stays in the brackets. So this X right here, this X squared right there, is forming the quadratic equation. And remember, our quadratic equation is ax2 plus bx plus c equals 0. So it's starting to form our quadratic equation. So if we get this x squared, we know we're going to be using this case. Okay, we're going to be using the quadratic method. So from there, we are going to expand and get rid of our brackets. So we'll get 0.0625 minus 0.0625x equals x squared. And now we're just going to arrange this in our quadratic equation, which means 0 is going to equal x squared plus 0.0625x minus 0.0625. So we just arranged this equation here into our quadratic equation. So from there, we are going to use this information and put it into our quadratic formula. So I'm just going to scroll down a little bit. So we're going to put this information here into our quadratic formula, which we know our quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac. Divide that all by 2a. And you must memorize our quadratic formula, okay? That's something that it should be easy to remember because you've used it in math, but you must memorize that equation, okay? So given our information that we found and put into our quadratic equation, we can put that into our quadratic formula, and we are going to keep out any x. whether it's in A, B, or C, we're going to keep out our x. So therefore, we'll get x equals negative 0.0625 plus or minus the square root of 0.0625 squared minus 1. So x, if it's just by itself, is going to be 1. Bracket 0.0625. Divide this all by 2 times 1. So please make sure that you are filling this in. Please make sure that you're filling in all of this information into your equation. So from there, we can solve for our square root. So leave our negative b here, 0.0625 plus or minus stays, and solve everything under our square root, which is going to give us 0.2539. And then solve our denominator, which was 2, because 2 times 1 is 2. And then from there, we can get rid of our square root, so 0.0625 plus or minus 0.50389. It's best to kind of keep numbers long as well as have more steps throughout this, because the more steps we have, the less likely to have an error. So keep this nice and long. And then from here, because we have our plus or minus, we are going to separate and give ourselves 2 answers that could possibly happen. So our one side, if we were to do positive, and the other side, if we were to do negative, so subtract them or add them, we would get 0. Oh my goodness, what just happened? Hold on. I apologize. I don't know why all of a sudden this is not working. Yeah, 0.220695. And then if we were to subtract them, we would get negative 0.28. And because this is a negative, it doesn't make sense, so it is excluded. We're not going to use negatives. So this is our ABC. We just use that. And now step 3 is use the x values to solve for the equilibrium concentrations and round to the appropriate number of significant figures. So separating our work out, we have PCl5, the equivalent equals 1.0 minus x, which is 1.0 minus what we just found, our positive value, which was 0.220695, is going to give us 0.779 moles. Then we do PCl3, which is x, which is going to be 0.221 moles. And then Cl2 equivalence is also x, which is 0.221 moles. Okay, so given our values here and what we just found, we can check to see if our answers are correct by subbing it back into our KC. So given these values that were found, we plug it back into our KC equation, and we will get 0.0627, which is very close to the KC that was given at the very beginning, okay, which was 0.0625. Very, very close, so therefore we know that it is correct. So we can say that we did the correct thing here. So that's our first way that we can do it. The second is the square root method. So we have our equilibrium constant for the following is 56. If 2 moles each of H2 and I2 is placed in a flask, what is the equilibrium concentration of H2, I2, and HI? So first step, always fill in our ice table. So we have 2.00 moles of both our H2 and I2. We don't know our products, but we know our ratio. So we have negative x, and then 2x. Which means we're going to have 2.00 minus x, 2.00 minus x, and then we'll have 2x. So ice table is now filled in. Now we can use the KC to solve for x. So our first step, always write out into our KC expression, what is it? So therefore, we're gonna have our KC is equal to HI squared, and then H2, and then I2. So given this information, we are going to take our KC value, which is 56. We're also going to take our change in concentration values. So we have 2x squared over 2 minus x, 2 minus x. So given this information, if we were to expand these two values out, we would get 4x squared, okay? And then we would also get our 2 minus x squared, okay? We're not going to get rid of our brackets in our denominator. We're gonna keep it the way it is written here. And then from there, if we were to take the square root now of everything, so square root of 56 and square root of our fraction here, we would get plus or minus 7.48, which is square root of 56. And then 4x squared would be 2x, because we're trying to get rid of these squared, over 2 minus x. Okay, so we removed the squared by square rooting it, and we were left with the following. From there, we can do our plus and minus. So if we were to do positive 7.48 equals our 2x over x minus, or 2 minus x, we would have to multiply our 2 minus x by both sides, and we'll get 7.48 multiplied by 2 minus x equals 2x. From there, we would get our 14.96 minus 7.48x equals 2x. And then we would get, from there, if we were to rearrange, because this is x, it goes on the other side, we'll be left with 14.96 equals our 2x plus 7.48x, which would give us 9.48x and 14.96. And if you divide both by 9.48, our x would be 1.58 moles. Now we do the same for the other. It's negative 7.48 equals 2x over 2 minus x. Then we move this to both sides and multiply. We will get, obviously, negative 14.96 plus 7.48x equals 2x. Move this over, we get negative 14.96 equals 2x minus 7.4. Oh my goodness, why does it keep failing on me? I'm sorry. Try to answer the following question. Give me a minute. Let's see if I can figure out what's going on, why this keeps dying on me. Give it a second. Try to solve this. What do we get for x? Take a moment. Okay. 1.48x. Skipping our steps a little bit, we'll get x equals negative, or positive, sorry. Oh my goodness. Skipping our steps a little bit, we'll get 2.73 moles. So this number here, this 2.73, this is larger. So this is a large number. It's larger than 2. So because it's such a large number, we're actually not going to use it. So therefore, we are going to be using the positive value when we added them, which was 1.58 moles. So we're gonna be using that value. So because it's greater than 2, we're not gonna use it because it's too big for us. So skipping over a few of these slides because it's just extra room. Step 3 says use the value of x that we just found, that 1.58, to solve for the equilibrium concentrations. So given our information, we have our H2 equilibrium, which was 2.00 minus x equals 2.00 minus 1.58, which is going to give us 0.420 moles. Then we have our I2, which is the exact same thing. So our answer is going to be 0.420 moles. And then our HI equilibrium is 2x, which is equal to 2 times 1.58, which is going to be 3.16 moles. So given all of this and all that we have found so far, we are able to determine and check our answers to check if it is correct. So plugging our values that we had found, so all of these values that we had just found here into our expression, and we can determine that it is indeed very close to what our original Kc value is, and therefore we're correct. The last step is our approximation. So approximation is when it's very, very small. Our Kc is very small. So in this situation, we have -7. That means our Kc is going to be super duper small. So we're going to use this method if it is small. Okay, so given the information here, we have to fill in our ice table like normal. So we have our 1 mole of CO2 is placed in a 2-liter vessel. So because it is in a 2-liter vessel, we need to look how many moles in 1 liter. Okay, we want it to be in 1 liter. So therefore, we're going to divide it by 2. So 1 mole is going to give us 0.500 moles. Going to give us 0 and 0. Our change is -2x, 2x, and then x, which is going to be 0.500, or 0.500 minus 2x, 2x, and x. So given our information here, we can use the Kc and determine if the approximation method can be used. So we know the value is very small, and so therefore we can use it. So Kc is going to be our CO2, O2 divided by CO2, 2. So given our information, we're going to plug in our values. So our Kc was 6.40 times 10 to the -7. We had 2x squared x divided by 0.5 minus 2x squared. Now, based off of this information, okay, we can get 6.40 times 10 -7. If we were to expand out this, okay, we would get 4x to the power of 3. But because this is an approximation method, this x at the bottom is going to be neglected. Okay, we're going to neglect this x value because Kc is already so small that if we subtract x by our 0.5, it's not going to make a difference. So we're going to neglect it. We're going to remove it from our information, and therefore we will just be left with 0.5 to the power of 2. Okay? So given this information, expanding out our 0.5 to the power of 2, we will get 0.25. And therefore, we have to now multiply our left side and right side by 0.25. So 6.40 times 10 to the power of -7 times 0.25 equals 4x to the power of 3. We will get our value okay, of 1.6 times 10 to the -7 equals 4x to the power of 3. Divide all by 4. Left us with x3. And then we'll get 4.0 times 10 to the -8. And then if we square root all by 3, we will get 3.42 times 10 to the -3 will be equal to x. So based off of this information here, plugging our information in, we will get CO2 equilibrium is 0.5 minus 2x, 0.5 minus 2, which is 3.42 times 10 to the power of -3, which is going to give us 0.49316 moles. O2 was X, which means it's going to be 3.42 times 10 to the -3. And then CO is 2X, which is 2 times 3.42 times 10 to the -3 is going to give us 6.84 times 10 to the -3 moles. So now, given our values, we are going to prove that the approximation method can be used, and you must do this all the time. If it is not fulfilled, then you have to use one of the other methods. So you have to calculate the percent error. So you're going to take the reactant initial or minus the reactant equilibrium, divide by the reactant initial times 100. So you can only use this if percent error is going to be equal or less than 5%. Okay, so the reason for that is that if it is less than 5 or equal to 5%, then that means the initial concentration of the reactants is going to be really, really close to equilibrium in comparison to the reaction concentration of the products. So, given our information that we have found, okay, our initial concentration of CO2 was 0.500. The CO2 equilibrium was 0.493, so we're going to take that percent error, and it's going to be the reactant initial minus reactant equilibrium, divide by reactant initial times 100%. So we're going to take 0.500 minus 0.493 divided by 0.500, all times 100 is going to be 1.4%. So therefore, it is less than 5. We know that this method works, thank goodness, because we did all that work. And unfortunately, that is what's going to happen. You have to do all the steps, and then sometimes it doesn't work, and you have to use a different method. So it worked. We can continue. So we're going to use the value to solve for x using our information. And we did this already, obviously, because we were able to round the appropriate numbers and values. And then step 6 is check your work. So plugging in the values that we have found back into our KC, and it is pretty darn close. So therefore, we know it is correct.